And welcome to SanfordFlipMath. We are working on pre-calculus, functions and graphs, etc. We are just starting chapter 3, which is about exponential functions and then by extension logarithmic functions. We are just getting started. The examples and content we're working in is from the pre-calculus book by Demana, Foley, Kennedy, 4th or 5th edition. And we are going to look at again, as I said, exponential functions. And I need to make a little distinction here. Polynomial functions and monomial functions are kind of like in this form, also power functions. Okay, and worth noting that, excuse me, we have a variable as the base. Okay, and then that's raised to some sort of an exponent, which is a number, okay, or a constant. Okay, and I need to make a distinction between that and an exponential function. Exponential functions also have exponents, but that's not where instead of the exponents being a number, the exponent is involving a variable. Okay, so this is an example of an exponential function. Note that the base now is a number, and the exponent is a variable, or at least has a variable in it. Okay, so that's kind of the distinction. So quick example would be like y equals 3 times 2 to the x is exponential. Y equals 3 times x squared is a power function or a monomial. Okay, so that's where we're at. Excuse me. Okay, so what we need to do is kind of play around with exponential functions for a minute so we can kind of get a feel for how things act. So what I'd like to do is I'm going to go ahead and take this 3 times 2 to the x, and we're just going to make a little bit more room. In fact, well, let me just go to the next slide. How's that sound? Okay. Oh, well, we'll play around with this and it'll work. Okay. So again, I just did 3 times 2 to the x. Okay. And we're going to make a little table of values here. So like -2, -1, 0, 1, 2. And you're going to have to remember some rules about exponents here. Okay, so for instance, I'm going to start with 1 because I think that's easier to work with. 3 times 2 to the 1, well 2 to the 1 is 2, so this is 3 times 2, also known as 6. 3 times 2 to the second would be 3 times 4. Just a reminder that exponents have to be dealt with before we do any multiplying. Okay, what about 0? Well, 3 times 2 to the 0. Okay, now just a little reminder here that anything to the 0 power is 1, just long as the base is not equal to 0. 0 to the 0 is what's called indeterminate. And it's kind of like undefined. It's not exactly the same. So 3 times 2 to the 1, or 2 to the 0, is 3 times 1, which is 3. Okay, and then 3 times 2 to the -1. Well, the thing you need to remember about -1 for an exponent is it means reciprocal. So that means 3 over 2, or if you'd prefer, 1.5. Okay, and last one for this list, 3 times 2 to the -2 would be 3 times 1 over 2 squared, or 3 times 1/4, also known as 3/4, or 0.75. Well, some things to notice here. As I'm going from x value to x value, counting by ones, notice what the y value is doing. 0.75 times 2, 1.5 times 2, 3 times 2, 6 times 2. And it should make sense that every time I increase this exponent by 1, I'm multiplying by another factor of 2. Okay, and this really goes to kind of a numeric understanding of what's going on. And so I'm going to do a little graph of this. Okay, so that's 12, 10, this will be 5. Okay. Okay, so what we're looking at, 0, 3. I guess I'll make this in red. Excuse me. 0, 3, 1, 6, 2, 12. Negative 1 had 1.5, and negative 2 had 0.75. So what's happening is every time I go to the next x value, I end up doubling, or times 2. And again, that's because this base was 2. Okay, and so it looks something like that. Okay, now a couple little questions that I have. First of all, what happens as x goes to negative infinity? What's y doing? Related question. When does y equals 3 times 2 to the x cross the x-axis? So as x becomes more and more negative, well, then I end up doing like 1 over 2 to the third if x is negative 3. 1 over 2 to the fourth, 1 over 2 to the fifth, 1 over 2 to the... These numbers get, as the exponents get bigger and bigger, 2 to this power gets bigger and bigger, which means our denominator gets bigger. And if I do 1 over a bigger and bigger number, the answer is getting smaller and smaller. So what number is that actually approaching? And what you need to know and need to understand and think about is the fact that it actually approaches the x-axis. The y is getting closer and closer to 0, and it never actually touches it. Okay, so y equals 0 is a horizontal asymptote, and that's kind of a big deal. Okay, and since that's true, this graph never crosses the x-axis. It doesn't happen. Okay, now you can make it cross the x-axis by doing some, shifting up or down, like we've done back in chapter 1. Minus 2 on the end of it, and then the whole thing shifts down or something like that. But there is this asymptote. Okay, y equals 0. That's pretty standard for any equation in this form. Y equals 0 is a horizontal asymptote. Okay, one other issue with this form that I need to make a big stink about. We are always going to have b values, the base. Okay, so remember that, again, this is the form we're talking about. Our base values are always going to be positive. Okay, so note that b is not going to be 0. If I have b equals 0, then I'd be doing y equals a times 0 to some power, which is just going to be 0 anyway, so that's not very exciting. Okay, we don't want that. If b was a negative, then I'd be doing stuff like, so let's say I had 3 times negative 2 to the x. Depending on the power that x was, depending on the x value, I'd be switching between positive and negative answers. So like if x was 0, this would be 3 times 2 to the 0, which is 3 times 1, which is 3. If I do 3 times negative 2 to the 1, this comes out negative 6. To the second power, this comes out positive 12. To the third power, this ends up being negative 24. And so the signs are alternating, and that's weird. And so instead of a graph looking like this, the graph would be kind of doing this, this weird double kind of thing. So it'd be almost like 2 separate curves, and it's just really weird. So we're not going to do that. So the bases are always going to be positive. They're not going to be 0. Now I should warn you though that the base can be a fraction. Okay, so I want to look at one more on this slide, and then we'll go from there. So I'm going to do the same exact equation, only instead of 2 to the x, it's 1/2 to the x. Okay, quick little set of points here. And I'm going to go faster this time because I'm a little concerned about time. So 3 times 1/2 to the negative 2. The negative flips it. So this becomes 2 squared. So 3 times 4 is 12. If I put in -1, the negative again does the reciprocal, so this becomes 6. 1/2 to the 0 is still 1. 1 times 3 is still 3. Now if for 1, if I do 3 times 1/2 to the 1, this is now 3/2. Now these numbers really should look familiar. They're actually the same exact numbers that we did before. They're just switched in order. Okay, so notice that they're the same numbers, just switched in order. Now watch what this does to the graph. Okay, so -2, 12, -1, 6. It's probably supposed to be there, sorry. Okay, 0, 3, 1, 3/2, or 1/2, 2, 3/4. Okay, and notice what's happening here. Notice that it's the exact same graph, only backwards. Okay. Okay, so y equals 0, still a horizontal asymptote. Also worth noting that 0, 3 was the y-intercept for both. Sorry. Okay. Okay, quick little note. I'm going to write down a little list of things that you want to be able to note from this. If I'm looking at an equation, y equals ab to the x, 0a is going to be your y-intercept. A is also referred to as the initial value. And the reason it's called the initial value is oftentimes x is about time for exponential functions. If x is about time, then when time is 0, that's when we start out, the initial, the beginning. Okay? Y equals 0 is a horizontal asymptote for any equation in this form. If b is bigger than 1, we're multiplying consistently by a number bigger than 1, it is called exponential growth. If b is less than 1, it is called exponential decay. Now, a quick little disclaimer. Remember we said that the bases are always going to be positive. So what we mean is if it's between 0 and 1. Okay, and so we're saying basically either there's a negative exponent or the base is a fraction. And now by a fraction, I mean a fraction less than 1. Okay, it's implied by saying less than 1 anyway, but I just want you to hear that idea of fraction in there, so like the 1/2 to a power. Okay, so bases are always going to be positive, and this is kind of a little disclaimer. Quick note, domain, all real numbers. Range, well, the bottom is the asymptote. Okay, so that's kind of a quick little recap or overview of all of the important features of an exponential function. Okay, I think this was form and limitations, so I think we're good there. And we did that already. Okay, domain. Okay, so I just want to do another one real quick. Okay, so y equals 5 times, let's do 0.8 to the x. Okay, now what I'm going to do, I like domain, range, any asymptotes, vertical asymptotes, horizontal asymptotes, end behavior, odd, even, neither. I don't think that's really an issue here. I don't remember what else I need on this list. Oh, increasing, decreasing. Okay, and we'll do a little graph. Okay, so this list should look fairly familiar. Okay, if I do a little table of values, I'm going to do a very little table of values. -1, 0, 1. 0 is going to be 5 because 0.8 to any power, or 0.8 to the 0 power is 1. 0.8 to the 1 is 0.8 times 5 would be 4. And to the -1, well, that'd be 5 over 0.8, which is the same thing as 5 over 4/5, so that's 25/4, also known as 6 1/4. Okay. All right, so just a little sketch of what's going on so far. 1, 2, 3, 0, 5, 6 1/4, and 1, 4. This is it. Okay, so this is called exponential decay because it is going down. Decay is when things go down or go away. This is exponential decay. And again, that base was between 0 and 1, so that's not a surprise. So if we consistently or continuously multiply by a number smaller than 1, things get smaller. Domain, all real numbers. Range, greater than 0. Vertical asymptote, none. Horizontal asymptote, y equals 0. As x approaches negative infinity, the y's are getting bigger and bigger. As x approaches positive infinity, the y's are approaching 0. There is no symmetry over the x-axis, y-axis, or at 0, 0. And this particular one is decreasing over all real numbers because it is exponential decay.